Yeah, thank you. Thank you for your nice introduction and then for this invitation for the talk. So as told, I am Ashok Kumar from IST Trivandrum, and today I'll be talking about some of the recent work on structured spatial quantum correlation in bright space light. And before I go to content of my talk, I would like to just a little tell about what we do and what we have in IST. So we have developed in IST like a dedicated quantum lab, or we call that quantum optical technology lab, where we are mainly working on different aspects of quantum technologies. So we generate squeeze light, entangled light in our lab, and then we use that for different application, as said, quantum sensing, metrology, imaging, cryptography, and communication. And then, of course, we generate these squeeze light, and then we structure those light and do a lot of stuff with those kind of squeeze light. And then, moreover, toward the teaching side, we have dedicated master program in quantum technology. Since 2022, we have started it. And then, of course, other than that, we have different areas of teaching where we teach aerospace engineering, avionics, engineering physics, and MTech and all. So many programs we have here in IST. So now coming to the actual content of my talk, that is structured spatial quantum correlation in bright squeeze light. So before going to the actual content, I must tell you that why we are interested in this kind of research and why do we do, like, one thing is, why do we care about squeeze light and why do we care about spatial quantum correlations? For that, I'll give you a brief motivation. If you think about squeeze light, and then if you think about recent quantum optical technologies, or rather quantum technologies, then you can find squeeze light everywhere. For example, one of the, this biggest experiment of 21st century, that's LIGO, gravitational wave detector, they are getting benefit from squeeze light to detect the signal beyond the short noise limit, or gravitational wave signal beyond the short noise limit. There also they are getting help from the squeeze light. On the other hand, the computation part, if you look at the photonic-based quantum computation, then people use so many squeezers or squeeze light sources and then do the computational task with squeeze light. That's why the squeeze light is important for the quantum computation application, as well as the communication. If you look at the quantum communication aspect, the quantum correlation carried by squeeze light can be used for cryptography and communication application. So these are the broad areas where you can think of your squeeze light could be useful. On the other hand, now just narrowing down, we are looking at the spatial quantum correlation of squeeze light. And then here also we have to understand, why do we care about spatial quantum correlations in squeeze light? So spatial quantum correlation in squeeze light, they have twofold application. In one side, they are very important in the fundamental point of view. If fundamental point of view means if you want to look at the fundamental test of quantum information theory, or if you want to look at the EPR kind of paradox, or you want to check the entanglement test, then you can use spatial quantum correlations as your resources. And then regarding this, I'm showing one of our most recent work, it's like 4 years back. Of course, other groups also have done this, but this is one of the most recent paper where this kind of fundamental tests, like EPR kind of experiments, were done with the squeeze light. Not only squeeze light, the one more important aspect we work with the bright squeeze light or macroscopic twin beams. And then here we have shown that, of course, indeed you can use these kind of systems for testing the EPR paradox. I'm not going to go to detail of this work here because this is not the focus, but just I want to motivate that this could be useful for very, very fundamental studies. On the other hand, of course, application point of view also, these spatial quantum correlations holds a great promise. For example, for quantum imaging and sensing, if you want to improve the imaging or resolution, spatial resolution, then you need to get the help from spatial quantum correlations. That's why they are important. On the other hand, if you want to look at quantum communication or quantum cryptography, where you want to encrypt your information securely, then you can use again a spatial quantum correlation degree of freedom. And then so that holds for the quantum information processing also. So along these lines, if you think of, then spatial quantum correlations could be greatly beneficial. And then at the same theme, also we have recently published a Science Advances, where we have used these spatial quantum correlation properties of squeeze light to encode information. We have securely encoded some of the information in the squeeze light we generate, and then we recover that information with a great fidelity. This is one of the very recent work we have done toward the quantum cryptography application. So that sets a stage that, you know, why do we care about these things? And then, of course, these are not focus of my talk today. My focus of talk will be only on the spatial quantum correlations and what we are doing, what new we are doing along these directions. So with this brief motivation, I would give you an outline of my talk. So as I see, there could be many of the students who are not aware of what is squeeze light. So I thought I'll give you a brief introduction of what is a squeeze light and how do we generate this squeeze light. In particular, in our lab, we generate something we call bright squeeze light or entangled light. And then the process that we are using for generation is the four-way mixing process. And we'll discuss about that process. And then once we generate or we show that how we are generating squeeze light, then we are structuring those squeeze light. We'll show how we are structuring those squeeze light or making different structure in squeeze light. And then we'll show some of their interesting properties, that self-healing properties. We'll discuss about that. And later we will look at the spatial quantum correlation properties in those structured light. And then, of course, we will look at their dynamics. And here you will see some interesting features where you can see that the spatial quantum correlation can migrate from localized regime to delocalized regime. I'll elaborate that little details. And then, and the last, I will conclude my talk with the very, very fresh result that we have got last week, that we have done some self-healing of quantum correlations that I'll discuss today. And then finally, I'll conclude my talk. So now, okay, coming to very basic, of course, this is a textbook thing. So what is squeeze light? So squeeze light is not really very strange. You can very easily understood that. You know, if you have an electric field, you know that an electric field can be written in sine and cosine components. And then, of course, I can write an electric field operator, and then electric field operator can have this sine and cosine component, and then corresponding operators. And then interesting about these operators, which are prefactor of this sine and cosine component, these components we call quadratures. And these quadrature components are like position and momentum variable. They are canonically conjugate variable. Or if you look at their commutation relation, it's not equal to 0. That means if it is not equal to 0, that means they have to follow a Heisenberg uncertainty principle as shown here actually. And then if you look at the Heisenberg uncertainty principle, then there is a greater equality, or there's an equality sign. And then one thing I must tell you here, if you generate some state, if you generate some form of state that can have electric fields such that the uncertainty in the measurement of this quadrature and then uncertainty in measurement of this quadrature, if it is equal and equal to the minimum allowed by Heisenberg's uncertainty principle, these kind of states we call coherent state. These kind of states we call coherent state, and this limit we call short noise limit or standard quantum. So, and if you look at the phase space diagram of the noise of this kind of state, then it look like this. Because the uncertainty in either of the quadrature is equal, then uncertainty blob will be like a disk. Now, of course, this is a classical limit. This is a classical limit, and this is a coherent state. And then if I ask you, or if I tell you example, then if you consider a typical laser beam is behaving, or the photons from laser beam behaves like that they are in approximately in a coherent state. Now the question is, can we have any state in which the noise is less than the standard quantum limit? So yes, indeed, we can generate, or we can have some state in which noise in either of the variable or canonically conjugate variable is less than the standard quantum limit. But of course, if one variable is having less, then other variable will have more, because it has to obey Heisenberg uncertainty principle. And if we have this kind of state we call squeeze state. And when we say that squeeze, what is being squeezing? Squeezing is like a reduction in noise. Noise is being squeezed actually. And then this is your short noise limit. And then you can say that this side noise is reduced. On the other hand, this side noise is reduced. And then of course you can generate squeeze state in any direction noise to be reduced. So you can do by changing your experimental parameters. Now, of course, this is the definition of squeeze light. Now, how do we generate this squeeze light? Then if you ask a theoretician, then theoretician will say that, of course, you take a squeezing operator. You take a vacuum or coherent state and then pass that to a squeezer, which is nothing but this kind of operator. And then at the end, you get this. But now, if you carefully look at what is this operator, this operator contains a square and a dagger square. These are the annihilation and creation operator. The squeezer is doing nothing but it is either creating or annihilating pair of photons. And then if you have a system that creates a pair of photon or annihilates a pair of photon, that means you can generate squeeze light with that system. Moreover, if you look at in terms of the photon number, if you look at the photon number picture, then if you look at the photon number distribution in a coherent state, for example, laser beam, then you will see that they follow the Poissonian distribution. If you look at the photon number in the photon number statistics in a laser beam, they are always random. You don't have a ordered distribution. On the other hand, if you have an amplitude squeeze light, then they will have really periodic or very ordered way the photons will arrive to your detector. Now, so here what we said, as I said, you can create a pair of photon or annihilate a pair of photon, and then these two photons can go to the same mode or same beam. But in general, it need not to be. You can create a pair of photon by this operator, and these two photons you can send to two different modes, two different spatial mode. And if you do that, then these kind of states we call two-mode squeeze state, or we call them twin beams also. So what happens, if you look at we are generating a pair of photon and they are going to two modes, which initially didn't have anything. Initially, they had vacuum. They have vacuum, but you are generating or you are creating pair of photon randomly to those modes. That means you are intrinsically increasing their noise. Initially, if you look at their individual noise, you are increasing because you are just pumping photons here actually. But interestingly, if you look at their quadrature behavior, quadrature correlations, if you look at what is the relation of x1 and x2, if you look at x1 and x2, you see the squeezing in the difference quadrature. Similarly, if you look at y1 and y2, if you plot y1 and y2 quadrature, you see squeezing in the phase sum. So that means, this squeezing or noise reduction is happening because of the correlation. That means in those two-mode squeeze state, their quadratures are correlated. Now, if I ask you, or if I tell you, what is the photon number distribution in two-mode squeeze state, as I told you, so you are creating a pair of photon. If one photon is created, its partner has to be created in the down beam. But when this creation is happening, that's one completely random, because it's a probabilistic event actually. Once you generate, other will also be generated, but when it is generated, you are not sure. But once it is generated, down beam will also have same photon actually, or similar photon. Now, if you detect one beam and then you detect other beam, if you look at their photocurrent, then if the first beam has photocurrent distribution like this, and then of course the second detector is also detecting the same photon stream, then it will have also the same photocurrent. And now if you have like here common correlated noise, you have the photocurrent which is fluctuating. This fluctuation is like coming from your source itself. Now you can subtract out these common fluctuations, and then you can get a state which have really less fluctuation. So that's all about two-mode squeeze state. Now, how do we generate these beams in the lab? So there are, historically, people have been generating these kind of two-mode squeeze state by OPO, optical parametric oscillator, where they have a crystal and they pump their crystal by a strong laser beam, and they create a pair of beam out of it. And then these pair of beam they put in a cavity, and then they generate their two-mode squeeze state, or the single mode squeeze state, or whatever squeeze state they generate like this way. Now, what we do, we use something different process. We use a four-way mixing process. Here it's like it's a 3-photon process. You absorb one, emit two. But another process also, another nonlinear optical process also you can use, where you absorb 2 photons and then emit 2 photons. Ultimately, you are emitting 2 photons. We care about these 2 photons. And these 2 photons, of course, they are emitted at the same time. They are highly correlated, or they carry quantum correlation property. Now, in our lab, what we do, we generate, of course, we use four-way mixing to generate these twin beams. And then four-way mixing we do in a configuration we call double lambda configuration. What we do in that configuration, so we will tell you that we use a strong laser beam, and then we make a strong pump beam and a weak probe beam, and then we interact these laser beam with the atoms, hot atoms. Basically, we have rubidium atoms, and then inside that rubidium atom, the four-way mixing process happens, and they generate twin beams actually. So if you look at the energy level diagram, what actually happens, so from the atom inside this rubidium cell, they absorb 2 photons from your pump beam. One is absorbed here, one is absorbed here, and then since 2 are absorbed due to energy conservation, 2 have to be emitted. Then one emits here, one emits here. Since they are emitting at the same time, they are quantum correlated. And then this process, the emission process, you enhance by using a seed probe beam, very weak probe beam. This is very powerful, let's say 500 milliwatt or more, but this is 100 microwatt. If you use very, very weak seed beam, this process gets stimulated, and then you get bright beams. You get bright, entangled, or squeezed light, which you can see even with your naked eyes. And then you can look at the quantum correlation in the macroscopic regime or with your conventional photodetector. So another aspect you must know that, of course, the energy has to be conserved. Other and conservation law, they have to conserve the momentum actually. Initially, since this process, 2 pump photons are absorbed and 2 are emitted, they have to conserve the momentum, linear momentum. So sum of this has to be equal to sum of these 2. So this conservation of linear momentum decides which direction these photons are emitted. And then this gives like a momentum correlations to these 2 photons actually. So this is about the source. And now I must tell you that how do we measure, of course, I'm telling about we generate squeeze light and all. How do we verify that this is squeeze light? Excuse me, this one minute. So yeah, I was talking about, okay, we generate a squeeze light, then how do we make sure that we are measuring squeezing, or how do we measure that? And then for that, what we do a very simple measurement. Squeezing is noise reduction beyond standard quantum limit. First, what we do, we set our standard quantum limit, and for setting the standard quantum limit, what we have a laser beam, and we do the we split laser beam into 2, and then we do balance detection, and we get a noise trace. What is the minimum noise that we can get from a laser, or that is our short noise limit. This is our short noise limit, and then this is our short noise limit, of course normalized to 0 because we have subtracted its mean. Then this is our short noise limit. Now, for the squeezing measurement, what we do, we do the same measurement strategy for the twin beams we are generating. We use a clean two photo detector, and then we do the balance detection, and then we check what is the noise we are getting. And this is the noise trace we have gotten earlier. So you see that our noise trace is below than the short noise limit or standard quantum limit. That shows that there is a squeezing. That is a noise reduction beyond the short noise limit or standard quantum limit. Here you can see that at that frequency, this noise analysis frequency, we have 9 dB of the squeezing, which shows like 87% noise reduction from your short noise limit or your classical limit. Now in IST also, of course, we have generated similar source based on the 4-way mixing and all. And then as of now, we have obtained this. This was my earlier work that I have done in US. And then now we are close to that. We have already obtained about 7 dB of squeezing in our lab. And then we are limited by some other technical issues, which is like, of course, we can always obtain about 10 dB of the squeezing if we just some technical things we have to resolve. But anyway, the point is we have already a source that can have 80% less noise than the classical limit. Now, of course, we are doing different kind of sources. Like for the same cell, we have two squeezer that can generate two sets of squeeze light, and then you can use two different application for two different squeezers. That is just a follow-up. Now coming to this first half was about the introduction of the squeeze light and then what we do on the squeeze light. Now I will tell you about what is the theme. As I told you, we are talking about the structured bright twin beams or structured squeeze light. And then for that, I will just introduce you about this work that we have recently finished. That is, we have generated this twin beams with some structure. When I said structured, then structured means these structured beams are very popular these days after, of course, about 30 years back in 1992, Les Allen gave that if you have a Laguerre-Gaussian modes, then these Laguerre-Gaussian modes can have orbital angular momentum. And then you need not to worry much about this long expression of Laguerre-Gaussian mode. You can think of any mode that can have azimuthal phase factor like exponential IL theta, then they can have orbital angular momentum. And these kind of beams are commonly known as structured beams. And how are they different from conventional laser? If you look at the conventional laser has a Gaussian intensity profile. And if you look at the phase distribution, is overall a uniform. And then if you look at the waist, their wavefront is like a planar wavefront. On the other hand, this Laguerre-Gaussian mode or structured beam that we are talking about, they have donut kind of profile. They have their intensity profile is having a donut, a dark at the center. And if you look at their phase profile, in their cross-section phase varies from, let's say, 0 to 2 pi or 0 to 4 pi and so on and so forth. And they have helical wavefront. They have, unlike the planar wavefront, they have helical wavefront. That's just this introduction to structured beam. But the important point that people are using for this structured beam is their orbital angular momentum properties, because orbital angular momentum property is not like spin angular momentum, which has only two basis sets. This orbital angular momentum can be, infinite basis set, because L can be minus infinity to plus infinity, any number it can have, any integer number it can have. So now, so as I told you, we already generated structured beam. We learned about structured. We already generated bright twin beams. We know now structured beam. Now we want to generate structured twin beam or structured squeeze light. This was our setup. So for generating structured beam, what we are doing, we are putting something called, to generate those structured light, we have something called vortex lens or spiral phase plate. One of our beams, this probe beam, we structured it basically. Then in that structuring process, what happens, it generates a partner. It generates the structured beam that is conserving the OM. Of course, this orbital angular momentum also during the process, any process we have, there are conservation law. Like linear momentum conservation, this orbital angular momentum also need to be conserved actually. So now, see, our system is like this. We have a laser beam, which is Gaussian beam, which is not structured. But a probe beam is a structured beam, which is having Laguerre-Gaussian beam. And then if you look at the four-way mixing process that we are talking about, in that four-way mixing process, 2 photons are absorbed, pump, and 2 are emitted. And then if you look at the pump beam initially, pump beams, they don't have any orbital angular momentum. Then what you expect? Because initially 2 are absorbed, 2 are emitted, then the orbital angular momentum has to be conserved. So they have to satisfy this conservation laws. So what we have done, so we have checked these conservation laws. So by inducing an orbital angular momentum to one of the twin beams, let's say we induce +3 orbital angular momentum to this beam, then other beam automatically gets -3 orbital angular momentum to conserve this OAM actually. So that's what we have done here. And then this is the way to verify the orbital angular momentum. This is like a tilted lens method developed in PRL-Ahmedabad. Now, other part we did, of course, in this one, the pump was not given any orbital angular momentum, but here in the next work, what we did, we gave orbital angular momentum to pump. We gave, let's say, -1 orbital angular momentum to pump. Then again, we have to follow the conservation law. Then in that case, again, they follow the same conservation laws. So after generation, the conjugate gets -2, but probe doesn't get, so that this -2 equals to -2. This again remains conserved. So we have shown that, of course, indeed, this four-way mixing process obeys the OAM conservation laws. This was, of course, a sanity check or just a starting for our next experiment. So that the experiment, what we wanted to do is, so earlier what it was known that these orbital angular momentum or Laguerre-Gaussian modes, they are very robust. It is known in the literature that they are very robust. And then, if you cut them, they heal. And if you let them propagate, they heal by themselves. And then we wanted to check whether if we generate these beams if we make OM beam here, and how this healing happens, or how they heal in case of bright twin beams or squeeze light. That's what we wanted. So this was our setup. Again, the similar setup, you need not to worry about much of it, because here strong pump, a weak interact and generate twin beams. So now in our first work, what we have done, we have first generated, or we started with a probe beam which is in a Laguerre-Gaussian mode, and then we blocked some part. We blocked 20% part of the probe beam. And then interestingly, if you look at the near field, we were looking, see, our probe beam that we were considering here, the probe beam we generated orbital angular momentum beam, and we clipped it. We blocked some part of it, and then use that part to have a four-way mixing. And then during the four-way mixing process, our conjugate also gets the same clip part. Though conjugate is generated after the process, but it gets, because it's stimulated by the probe, it gets the similar structure, but it's a clipped structure. And then we let them propagate. We let them propagate, and as soon as we propagate, and then in the far field, they again get the full donut. That shows the self-healing properties of those beams. And of course, we confirm their charge. One was +1, other was -1. That was confirmed in the interferometry. That's a very conventional technique to confirm the charge of OAM. And then this self-healing we understood by the energy distribution. As the beams travel, then the energy from the side, or just we did the Poynting vector analysis, and then in this way we knew how the energy is flowing, and then basically it is making heal this block beam. Of course, this was here, we blocked 20%. Now, later what we did, we blocked more part. We blocked about 40%. And then, of course, orbital angular momentum also we increase. What happens in that one also, see, we blocked +2, and then at the near field, since we conjugate is getting induced from the probe, we get the same structure in conjugate also. And then again propagating, while propagating, we got two donuts. Two donuts is signature of charge 2. And then here also two donuts. That means even after 40% beam blocking, you can reconstruct this orbital angular momentum. And then, of course, there has to be a limit. And then after that, what we did, we blocked 50% of the beam. And if we block the 50% beam, then after that blocking 50% beam, we could get only one donut or one donut or one charge out of two. We could get only one charge. That means it's a limit. It's limit. After that, it doesn't heal up to 40, 40, 45, 48% until we have done. It heals, but beyond 50, it doesn't. Now, of course, why we are doing that, the whole purpose of doing that is, I will show in the later slide, is see if first we want to see whether structures are healing or not. Once they are healing, look at the quantum correlation properties, whether they are healing or not. If they are healing, that will be indeed helpful for quantum communication or any quantum sensing application, because you have your information, somehow it was lost by some obstruction, and then you let them propagate, and then you get your information back. So that will be very important tool for quantum communication application. And then, of course, in the another follow-up work in this, there's the same structuring. We structured our pump also. Maybe I'll skip this part, but because the thing that I wanted to tell, it is clear in this slides. Now I will come to the another part. As I told you, so in this one we did not look at. We just look at the their spatial intensity profile. Here we have not talked about any quantum correlations. Now in the next task, what we did, can you check or can we comment anything about their quantum correlations property of these split beams? And this is the work we have finished recently. And this is very, very elaborate work where we have done theoretical as well as experimental understanding of spatial quantum correlation with structure twin beam. And then, of course, this is our structure. Our label diagram is like this. And as first, I would like to show you what we got in a spatial quantum correlation dynamics with the Gaussian pump beam when we did this analysis with the Gaussian beam, not the Laguerre-Gaussian beam, with the Gaussian beam. Then these were, of course, and then we were generating these twin beams, this probe and conjugate beams. We are generating them and we are letting them propagate. And then we are seeing how the spatial quantum correlation properties of these beams are evolving. Okay, so for that purpose, first we have done a theoretical analysis where we have looked at the 2-photon probability distribution. That means, we fix, as I told you, we are generating twin beams, right? We are generating one beam here, one beam here. And then we want to look at the spatial quantum correlation. A spatial quantum correlation means if I fix this point, and then because these are the pair of photons are emitted, one photon is emitted here, one photon is emitted here. So if I fix this photon, just I want to track where its partner is hitting. That's what I'm talking about, spatial quantum. In this spatial regime where its partner is hitting, that is all about spatial quantum correlation. It's not a temporal. I'm fixing, let's say I fix one point here, and where its photon is hitting here, where its photon is lying somewhere in this beam. That's what I mean by the spatial quantum correlation. So first we have done this analysis for the Gaussian beam, for the Gaussian pump case, and then we looked at first 2-photon probability distribution. That means if I have a conjugate photon here, where its partner is hitting, and then at the near field they have very, very localized localized distribution, or this is localized correlated distribution. Correlated means if you look at the one beam photon, other beam photon will be the same side at the same distance from origin. And then this is a localized behavior. And then as beam propagates, they smear out. These correlations smear out. And then if you look at the far field, they becomes ulta. They becomes like a, here they are correlated. They are correlated. If one is positive, other is also positive. But here they are negative. If one is positive, other is negative. It's going in a negative direction. So they are anti-correlated. These are the regions already known, like in the near field, you have a position correlation, far field, you have momentum correlation. On the other hand, this is like a 2-photon probability distribution. Now, if you look at the conditional probability means if you fix, as I told you, 1 photon in one beam, and what is the probability of finding its partner in another beam? If you look at in the conditional probability distribution, in the near field, if you fix 1 photon, then in other beam, it's to find the photon in other beam is very localized. You can find in very localized region. But as you go far, of course, it is being smeared out again. And then here, one interesting aspect I must tell you here also you can see that initially, let's say you found one beam you fix, and then if you look at the partner in the other beam, they lie in the same side. Let's say this is the vertical line denotes my origin. They lie at the same side. The correlation peak is at the same side. But if you move away, then correlation peak shifts to the negative side. That is the consequence of anti-correlation. So this is with the Gaussian pump. This was known earlier. But what was not known earlier with the detailed theoretical description is this work actually. So this is what we have done with the Laguerre-Gaussian pump. In the Laguerre-Gaussian pump, the result for the near field means where my source is placed, it's very similar to what we got with the Gaussian. But if you look at the far field, in the far field, the correlation distribution starts getting again kind of donut shape. Here, if you look at with the Gaussian beam, your correlation distributions or the probability of finding the photon is in a Gaussian regime only. And it's just a localized peak here. But on the other hand, if you have a Laguerre-Gaussian pump, your correlations are distributed throughout whole beam. So you get a non-localized correlation. It's not if I fix 1 photon, another photon can be anywhere. So it doesn't have a localized distribution. That's what we found in the Laguerre-Gaussian pump. This one was our theoretical result. Now to test the same thing in the experiment, what we did, of course, we want to look at different part of the beam. Let's say we have twin beams here. We generated twin beams here. I have detected 1 photon. What is the probability of detecting its or where is the probability of detecting its partner? That's my target, right? So I detect 1 photon, and where in this beam I can detect its partner? That is the probability I want to look at it. So for that, what we have done, we generated twin beams, and then we started clipping the twin beams and looking there. See, this big region we are just clipping so that if 1 photon is here, its partner is here. If I get the partner, I can see some quantum correlation, or I can see some squeezing, noise reduction below the short noise limit, because that is because of the correlated nature of the beams. So if I cut this, if I get the squeezing, that means they are localized. If I say that 1 photon is here, another photon can be here, then if I cut it, then the correlation will be lost, and then I will not get my squeezing. The whole idea is clipping the beam and checking squeezing to check the correlation. That's the strategy we have adapted. And then these are the results. What we have done. So in first case is as a usual case for a Gaussian pump and Laguerre-Gaussian probe. For the Gaussian pump, so this this region, the shaded region, is quantum region. If I see any noise In this region, that shows the quantum nature. If anything above this shows the classical nature. So now, if you look at our noise distribution, so we see we in the near field where we were expecting to have localized correlation. So we cut the beam up to 80% also, up to 80% beam clipping. We cut the beam 80%. Still, you can see quantum correlation. That means these quantum correlations are localized. That's how we are checking. And then localized and same side. And on the other hand, if you cut one beam from this side, other beam from this side, in the near field, you will not get any correlation, as has shown here actually. Because you know that in the near field, one is detected, other partner has to be detected at the same side. So that's what we have shown in this particular plot. And of course, we have shown the different traces are for different propagation distance. That is not needed for this talk here. Now, in the far field also, for the Gaussian trace, we said in the far field also, they are kind of localized. They are not as localized as the near field, but they are more or less localized. That's why even we clip the beam, we could see the quantum correlations. On the other hand, when we have a Laguerre-Gaussian pump, then in the near field, we could see here also with 80% clipping, we could see quantum correlation. We could see quantum correlation. We could see that means with 80% beam clipping, if I'm seeing the quantum correlation, that means in 20% only the quantum correlations are localized. On the other hand, if I look at the far field, if I just block the beam by 20%, my noise is shooting up beyond the short noise limit or above the short noise limit. So that means my quantum correlations, I'm not able to capture quantum correlation if I block 20% beam. That means my correlations are non-delocalized, as was shown by this. The correlations are everywhere. If I block this part also, that means I have lost some correlation that ultimately add noise to my system, and that is shown by this plot here. Okay, this is what I wanted to tell, and just I wanted to flash highlight very recent from last week. We are doing some very interesting work on structuring spatial quantum correlations, in which what we are doing, we are generating these bright twin beams or bright squeeze light with the structure, neither donut nor Gaussian, but some Spatial kind of beam. And then we are trying to see whether we can see the correlations in those patterns. And moreover, one thing interesting aspect of these pattern modes is in the classical optics, it was known that if you block one pattern, it self-heals. Whether the quantum correlation properties are also self-healing or not, that's what we have been checking. And then indeed, this was our initial beam. And then in the near field beam, we have clipped one of the petals, and then we let this propagate. And after propagating, then the beams, these petals are getting reconstructed. These petals are getting reconstructed, and this was the original beam. And we are getting again 4 petals. Now, in the reconstructed petals, we are checking whether we can see the squeezing or not. And indeed, here are our results. This was our short noise limit, and this was our squeezing with the whole beam, and this was our squeezing with the just these 2 petals. If I look at these 2 petals, you can still see the quantum correlation or squeezing. So that means indeed these petals which are being reconstructed while propagating, their quantum correlation properties are also being reconstructed. Of course, we have used more petal beam, and then we got the, like here, 6 petal beam we had generated, and then individual petals are also correlated. That's what we have done. And then later, just to play more around it, so we just block 2 petals. If we block 2 petals, and then even if you block 2 petals, if these beams you let them propagate, they again self-heals. the reason being of having that is these Spatial beams are solution of your Maxwell's equation, right? So if you have a clipped beam, it's not a solution. It's not a definite solution. It tries to go to its nearest solution, and that is the nearest fixed Spatial beam. And then if we looked at this again, the Spatial correlation, then we could see the squeezing. That means here also we have quantum correlation properties which are some right. Okay, yeah, this was my last slide. So okay, finally concluding. So what I talked in last 40-50 minutes, what I talked that, you know, you can generate bright squeeze light by using a four-way mixing in double lambda configuration in hot atoms that we are doing. And then of course we have generated this bright squeeze light with orbital angular momentum beams. We have Laguerre-Gaussian modes having squeezing, and then we have understood, or we have explained about self-healing properties of these structured bright twin beams. And later on we looked at the correlation dynamics, and then we saw that if you have a Laguerre-Gaussian pump beam, then it can give you delocalized far field correlation, which was localized in case of a Gaussian pump. And then very interestingly, or very recently, we have shown that you can generate twin Spatial beams, and then you can look at the multiple twins which are correlated, or just like a multiple twins which are correlated, and then you have multiple bipartite system together. So yeah, with this, I would like to acknowledge my students. This is my current group, and these are all my PhD students. And then for this, I would like to acknowledge Jaren and Chiran, who has been working for this project and the results presented here. And then I thank you all for your attention. If you have any question, I would like to take them.
Okay, so thank you very much for this, to the time presentation, very informative. So now it is open to the question from the participants.
Yeah, so can I ask one question?
Yes, sir. Yes, hello? Please, sir. Yes, sir. Yes, yes, please,
really, please. Very, very nice talk. You know, this about self-healing.
Yeah.
I know we are aware about self-healing in airy beams, but this beam also shows self-healing.
Yeah, it does. It does. In fact, last year I was in PRL. There was ADI also, and then I was giving some of the very preliminary result, and then he was mentioning, why don't you try airy beams? I said we tried, and then of course it was some of the earlier work in different regime people have done it. So I thought it's not better continue with that, and then it does that. Indeed, it does.
But you know, your beam self-heals in the near field limit, not in the far field, right?
No, in the far field. In the far field.
In the far field. Okay.
Yes. Okay. So another interesting, very interesting aspect is, as I was talking, this just last week result. These Spatials I have shown you, right? These Spatials are all correlated. These like a multiple bipartite system you have in the same system.
Correct.
So that we can use for further quantum information processing, because let's say I have 6 Spatials. It's like a 6 bipartite entanglement you are generating right away. And then it's not a limitation to 6 only. So we can generate as many as, and then by using some operation in future, we can use that just making all entangled together. Just a matter of some linear objects.
Just Snigdha, one more question. Sorry, others are not asking.
Yes.
I see. Also, you mentioned about that Maxwell equation, that finally it has to obey Maxwell equation, right?
Yes.
So does that imply that you can test quantum to classical transition?
So these beams, if you talk about the field, right? These fields are just, for example, Laguerre-Gaussian or Hermite-Gaussian. These families, ultimately, we look at their solution of paraxial wave equation, and then their solution. That's why they are transitioning to the nearest solution. Now, if we look at classical to quantum, then what we have to look at, I am not sure about that, but we can think about it.
We'll talk about that.
Yeah.
Thank you. Very nice.
Sure. Thank you.